and then share screen. Share screen here. Let's start. How about let's just start here. Okay, so just a quick review. As it yesterday we started to discuss the perceptron learning. Okay, this is the simplest case. Okay, and so you remember we discussed. So this represent vector. Okay, for the features. For features is it, so we have like x1, x2 to like xm. Is it each of the features? So this is individual feature. Visual features. Is it? And in artificial neuron, we say they are input signal. Is it? But in machine learning, we call them features. Is it? And you have y. Is it? And the y is regarding the target. Is it? So this is the target. Is the target. And we also learned we have that y hat. Is it? Y hat is predicted. So we use our learning, is it, to predict what it will be, is it? And this perceptron is for classification. Okay. So it's discrete value, not continuous. Okay. Okay, so that's the general science, is it? And then, so here the whole picture is, because you only know those features, is it? And you're going to use those features to predict, is it? It belongs to class 1 or not class 1, is it? It is that class or not that class. So we know the feature. So generally, so here the concept is, oh, how about we try to find some math expression, is it, to combine all of those features, is it? So we integrate all of those features. So we aggregate them, is it? So we do accumulation, is it, of the features. So that's why we have this concept, is it? I from 1 to m, is it? Then xi and wi, is it? And here we use linear, is it? Linear expression to represent, okay, to predict the target value. And this w is, we call it weight. Is it? So for each feature, you have the corresponding weight. Okay, if we already know the weight, so the weights are unknown. Because if we know the weights, we don't need to learn. So we can just directly use this expression to predict. So the problem is we don't know the weight. So we don't know the weight. Okay, and this, and in machine learning, we call it net input. Net input, is it? And then net input, generally we assign it to z, is it? And then we also have this phi, is it? Z, is it? And this we call it a decision function. Is it? And decision function is, can be 1 or -1, is it? And we call this unit step. So in perceptron, we use unit step function. Is it? And it is if z greater or equal than threshold. Is it? Otherwise, is it? Then it's not the class, is it? So this is the classification. Is it? So you use the decision function based on the net input, and the net input, if it's greater than certain threshold. Then later on, we said, okay, we can also move this threshold to the left side of the net input, is it? Then we updated it to I from 0 to n, is it? But be careful, okay, x0, okay, and the W0. Is it W0 is negative theta, is we call it bias, is it? And x0 is always 1, okay, it's not the feature. Then we update this as expression to, oh, still 1, negative 1, but here it's z greater or equal than 0, is it? But the problem is we don't know the weight, is it? So how do we find the optimal weight? Is it? That's comes the learning concept. Learning is learning what? So it's using large volume of data, is it? Of data, is it? To basically it's try out, is it? To try and find the optimal weights, is it? And the optimal weights, what do we mean? We mean that the prediction accuracy is going to be high enough. Is it meet your requirement? Is it? So that's the idea. So the weight we don't know. Is it? We unknown. Is it? But we can start with some, we can call it trial values. Is it trial values? Is it? And then with trial values, definitely your sigma I from 0 to m xi wi. Is it? This net input, is it? It will not be that accurate. Is it? It will not be. So then you get the y hat, is it? So it will not be that accurate, and then we can find what? We can find, so this is the real value, real one, is it? And minus the predicted one, is it? And we call it learning, and then times the delta wi, is it? And times the learning rate. So this is called the learning rate. And this delta W we keep updating, is it? We start with some initial trial values, is it? And then we are going to update. So update is W equals W plus delta W, is it? And you keep updating this, and it will make it more and more close to higher accuracy. Okay, then we can achieve our goal. So that's the general idea. So let's quickly go over. So the perceptron learning, is it? So over here, like we initialize the weights to some, generally it's some small random values, is it? And over here we need to be careful, okay? So if the superscript, is it? It represents some specific sample, okay? Specific sample. So for that sample, we will calculate its predicted y hat, is it? And then we can update the weights, is it? How do we update the weights? So here we have the formula, is it? The formula is the learning rate, so the real value minus the predicted value, and the times the corresponding. So this is that sample, is it? And this subscript J is for the J's feature, is it? And correspondingly, so this is J's feature, the corresponding weight, is it? It's weight. So the weight, we can see it's keep changing. Is it based on based on these two values, is it? And then we can update, is it? We get the latest weight, is it? Get the latest weight, and once you have the weight, then same thing, is it? Then you have that sigma xi and wi, is it? And based on this value, then you can predict if it's 1 or -1, is it? So you can come up with the y hat, is it? So gradually you may approach to some optimal value. So that's the concept of perceptron learning. And the perceptron learning, be careful, it must linear separable. Okay, it doesn't apply to non-linear separable classification, but later on we will learn this. Okay, so that's the idea about perceptron. And then let's go back to our code. So that's just a, where is my code? Hold on, this one. Code is here. Okay, and yesterday I remember we already went over this, is it? So we have that perceptron learning, we define it in a class, is it? In the class we have the constructor. So constructor, you need to define the learning rate, eta, is it? And the number of iterations, is it? And the random. And the fit is the training. So this is for the learning part. Okay, this is the learning part. Learning, okay. And with the learning, so with the learning, the goal is to find the weight, is it? So that's the goal. Goal to find optimal weight. Optimal weight, is it? Because if you find optimal weight, this is our xi, wi, is it? Then later on when you have a new signal, is it a new signal? Then you already have the optimum weight, is it? And we aggregate all of the features, is it? With its weight, then we can correctly predict. Is it correct? So that's why we need to find the optimum weight. And here we initial the weight. Initialize with some random number, some small random values. There's some small random values. And arrow at the beginning, of course, we don't have. That's why we put it a list, okay? And we also try to keep track the arrow situation, is it? So this loop, the inner loop, yesterday we already explained, is it? So basically what it does is to find the delta W, is it? Delta Wi, is it, equals the learning rate and y minus y hat, is it? Let's use J, okay, the feature. And then delta, not delta, it's xi, okay, the feature, is it? So this is, this is the I, this is J, okay. So this is how do we find the update. So this update means regarding those delta W, is it? Delta W. And after that, then you can get the corresponding weight. Is it corresponding weight? Corresponding weight. Okay, so that's for the inner loop. Okay, that's why it's loop through all features. Okay, so be careful. Okay, so all the features. Okay, and then we also have outer loop. Is it this outer loop? That outer loop is for what? Is we are trying to get optimal weight. Is it optimal weight? Okay, so that's oh, I'm sorry, that's not just a loop through all the features. So here I messed up. It's not a through feature. So this is a loop through all samples. All samples. Okay. And here, this two already taken care of features. Sorry, get messed up. So this is for features. For features. Okay, so the inner loop is a loop through all the samples. Okay, and the outer loop is try to find the optimal. Okay, because if you just use one iteration, it won't work. Okay, so that's why it needed to do the justification. Okay, so that's the that's the perceptron learning part, and we have net input and the prediction, so nothing new here. And then we started to discuss for the real data. That's a flower data, okay? Like I already explained yesterday. So this is from some classical machine learning repository, okay? And then next, let's see. This is regarding the plotting part. So I already posted the Python plotting. Okay, Python plotting, we mainly use the matplot library. Okay, the pyplot. So generally, when you do plotting, you need to import the pyplot. Okay, in the pyplot, and I have a video. I have a specific plotting unit on our course website. And over there, I have the class notes, okay, the Jupyter Notebook notes. And I also have the corresponding video, okay. So we are not going to go over here in class, and I recommend you watch the video on your own, okay. It's pretty straightforward. So here, let's take a look. Over here, so we have the data frame imported. So here we get that data frame, and we get the first 100 samples, the first 100 samples. And this target is the fifth column. The fifth column is a flower, is that setoso something. Versa color something, So that's regarding that part. Okay, regarding that part. So it's the fifth column. Okay, column number 4, but it's a fifth. Okay, and because over here, if you see, all of this is a string. Python string? So it won't work in machine learning. In machine learning, we already see we have a y, and the y hat it's 1 or -1, And we have that sigma, xi, mi, l, wi. It's all numeric values. So string won't work. So that's why over here, for your target value, you need to convert it to number. So here it says, oh, if it settles, so it will be -1. Otherwise, it will be 1. Okay, so that's how this works. And then for the features part. For the features part, it only take the data frame, the first one and the third one. Okay, third one. So we have the features here, okay? And then here it does the drawings. We can take a quick look at the drawing. Okay, we have those, So let's see. So here, what kind of drawing? It does the scatter drawing. Okay, so you just say scatter. Okay, so it will draw off the dots, So here it gives the value, the first feature. So feature 1, this is feature 2. Feature 2, two feature, and then to specify the color for this specific feature, and the marker look like what, and its label. Okay, the second one, same thing. Okay, this is for the second category of flower, And then we also have the for the x and y coordinates label, And this legend. So if we take a look at this plot, So this is the legend. This is the legend part. So if you have your label here in a pie plot, is it? If you define the label, it will automatically go to the legend when you specify the legend. And here it says where it's going to go, it's go to up left. Okay. So that's this plotting, okay? And this plotting then it shows. And from this plotting, we can clearly see the classification. It is linear separable, is it? Definitely this is linear separable. Is it linear separable, is it? So yeah, so it's very obvious, okay? And then let's see, how do we apply the perceptron learning, is it? So the very first you need to create an object of perceptron learning. So you define the learning rate. This is a learning rate, is it? It's 0.1, okay? Generally, learning rate is between 0 to 1, okay? And generally, we don't pick a very large number, okay? Generally, it's 0.001, 0. Like this scale, okay? And the number of iteration you want it to look, because sometimes it may never converge, is it? Then it takes forever to learn, is it? Then in that case, you just limit the number of iteration it will go through to learn, okay? So after that, we do learning. So generally, we always call the fit function to do learning. So this is learning. Okay, after learning, then it will come up with what? With all of the optimal weight, is it? Optimal weight. And if you recall that perceptron class, is it? Perceptron class, it also what? Keep track of the arrows, is it? So this is the arrow list. Is it arrow list for each iteration? Iteration. Is it for each iteration? It will keep track the arrows. Is it? And here we do the plot, pie plot. Is it? This is not scatter. This is curve. Okay. So plot. So the x coordinates the range, is it? Is a number of iterations. So number of iterations, is it? And the y is the arrows, the corresponding, is it? So we also have label, and then you do want the plot to be shown, okay? So that's the general about plotting. Then let's take a look. This plotting, is it? So this epic represents for iterations, is it? Iterations. Okay, and you can see the beginning, at the beginning, the number of updates means the arrows. The arrows, is it? And we can see at the beginning part, the arrow, is it? The arrow is high, is it? At the beginning. And when it reaches to iteration epoch 6, is it? The arrow kind of close to 0, is it? And it's not increase. So this is good, is it? So means the arrow getting a smaller and smaller arrow rate means your prediction, the accuracy is moving up, is it? And it's over here, it's kind of stable. Is it stable? Is it? You don't want a curve looks like this. That will never converge, is it? So this does converge, it's stable, is it? So that means it converges. Okay, so then that means this is a good result, is it? Okay, so that's regarding this. Then once we have the value, is it? So total data set, the data set size, if you recall, it's 150, is it? And we use the top 100 for learning. For learning, is it? Use the top 100 samples. So top 100 samples for learning, is it? And now I want to check, okay, if my prediction is correct, is it? Kind of like a testing, okay? So I use 100 ones, is it? The 100 ones, okay, it's Y value, is it? And I also can get its X value, is it? And I can call predict, is it? I call predict, and did you see I also output the result, is it? And you can see the result, it's pretty close, is it? It's correct, is it? So it's correctly predicted, is it? And the same thing, you can take the next 5 values, is it? The next 5 samples, next 5 samples, is it? Next 5 sample, and then you check if it's a certain kind of flower, is it? And we can see the result, is it? It's correctly, is it? It's also correctly predicted. So yeah, so looks like perceptron in this case works pretty good, is it? So that's regarding this example. And the last series is regarding some plotting. And if you're interested, you after class, you can take a look. And we will move on to the next part, sharing screen. Let me bring over the other one. Okay, so in the previous perceptron, so we define our own perceptron learning, is it? And basically, so Python machine learning, they have a very, very nice library, okay? And we call it sklearn here. So if we import this sklearn, we can do a lot of things, okay? For perceptron, we even don't need to use, to write our own, okay? But anyway, in the sklearn here, it imports the data set. sklearn, it also have some sample data set, okay? That iris, that one, it's also located in sklearn, okay? So over here, we get our data set from the sklearn, okay? Not the classical machine learning repository, okay? And then we try to get its features and its target, okay? Feature and the target, and it automatically, you know, over here, you can define, is it already taken care of? And then over here to check the size, is it? And total, we also have 150, is it? And the class label, it has 3. Is it? Because there are 3 types of flower. Is it? Here it says, okay, 0 represents setosa, 1 is for versicolor, and 2 is for virginicor, is it? So the 3 different color of flowers, okay? So anyway, here it shows for that iris classical example, you can also load the data set from sklearn, okay? And then next, as it's very good, okay? And simplify our work a lot. So over here, okay, over here, we use sklearn library again, but here is we do some model selection, okay? So what over here does it do import the train and test split. And in machine learning, we did this a lot, okay? In our previous example, we didn't do the data splitting, okay? So here the case is totally we have 150. Is it? So we have 150, is it? Samples in the data set, is it? So the train and the test split is you're going to split the data. So in this case, we specify the ratio going to be 70% for train and 30% for testing case, okay? So it will, so if we use this model, okay, train and split model, and then you specify the feature and the target, you specify the ratio, and then it's not always, you can use 0.2, 0.1, so it depends on your design, okay, or 0.35, it depends on your preference, okay? And then what it's going to do is it's going to use that 70% to do learning. Okay, and the 30% is going to test. So test your learning model's accuracy. Okay, so kind of like this. So that's for the train and test split. And then next, we can also do bin count, is it? So here you want to know how many in class 0, 1, and 2, is it? So we can see it's evenly distributed. Because later on, sometimes, because over here we want to do classifications. So if you want to do classification, you want to sample their class evenly distributed. So you don't want one take 90%, the other just take 10%. That's not going to be good for training, is it, for learning, etc. So that's why here you can see, oh, all 3 classes evenly distributed, is it? And then how about your train and the testing split, is it? It's also evenly distributed. So this is good regarding this part, okay? And then over here, there is another concept is with this sklearn, and later on we will learn why we do this. But over here, it's you use the pre-processing and you import the standard scalar. Okay, a standard scalar is because sometimes the samples features, okay, feature values may not be on the same scale, is it? So one sample, suppose, or one feature may be 0.01 scale, is it? Another feature, another one may be like 10,000 something. Then if you compare the scale, definitely not on the same level. Is it not on the same level? Just think about the effects. The effects on this, it's going to be huge. It's going to negatively, is it, impact the results, is it? So that's not going to be good. So over here, the goal is to make features in the same scale, scale level. Okay, so how do we do that? It's xi minus nu over sigma. So this is the mean value. Okay, and this is a standard deviation, is it? Then if you, for all features, if you do this kind of rescale, it will bring the features to the same scale. Okay, so that's the purpose for this. And the sklearn already provide us with that standard scalar. So you just create a standard scalar object, is it? And then you call the fit for the training data, is it? And after that, you also need to transform, okay? Be careful, you need to transform the train and the test, okay? Don't forget this. So the step is you first create the standard scalar object. So first you need to fit. So fit first, okay? Then transform. Then call transform. Okay, you need to transform. You see, this is the original scale, is it? Maybe 1,000. And after you transform, generally maybe 0 to 1. Everybody is 0 to 1, maybe, okay? So bring to the same scale, okay? So that's why your training, you need to have it train standard deviation? Is it testing also standard deviation? Is it make it to the same scale? Okay, and it won't impact Y. And then in sklearn, the linear model, okay, package, we can directly import the perceptron. So the perceptron learning is already included. It's some linear model, okay. Then you see, you can call perceptron, iteration, learning rate, is it? And then take a close look here, be careful, okay. So here when we do fit, okay, we fit with what? With the skilled data. The skilled data. Okay, skilled data. And then we can do predict. Is it? You can do predict. And when you do predict over here, be careful, okay? So when you call fit, you use train data. So this is train, okay? When you do predict, we use test data. Okay, we use test data. And then you can also check how many errors you have. Is it? So here it's misclassified samples. Is it? So your testing result is different from the prediction result. Is it? Total number of samples. Is it? And here it's just only 3 not correctly predicted. So the result, you can see it's pretty good. Is it? And then how do we know where our result is? Is it? So in sklearn, the metrics package, it also has the accuracy score. Okay, so you can also use this accuracy score. Hello? Hello? So anyone has a question? Okay, so anyway, so if you can also check how accuracy of a model is with this accuracy score. Is it? The accuracy score you just call the accuracy score, is it? And you plug in with test and prediction result. Okay. And with perceptron itself, it also has this accuracy score. Okay. Then in that case, you plug in your features, is it, with testing and the target testing. Okay, so this all regarding testing. Okay, so so someone, can you turn off your audio? Okay, so over here you can see for perceptron, we can also use the perceptron model directly from sklearn. Okay, so and then generally speaking, what the general steps is, you first you split data in train and test, you call that, is it? And after that, generally you can also make sure if your data is evenly distributed among different categories, different classes, okay? And after that, generally we need to do pre-processing, okay? This is just one of the pre-processing. Later on we will see more, okay? And this just bring off the data to the same scale, okay? And just to keep that in mind, when you do pre-processing, don't forget the transform, okay? We need transform. After that, then you can import the perceptron, is it, start the training, is it, start the training, and then call predict. And after you go home, you can try. If we don't do the standard scalar, okay, if we don't bring the data to the same scale, if you just use original train, you will find this result, the accuracy score is very, very low. Okay, very, very low. So after home, you can go try this, okay? But this result is pretty good, is it? It's 93%, okay? So that's regarding this one. And then next, let's move to another new topic today, the adaline. Let's first check if we have any question. Oh, no question. Okay. And then next, let's see another model. Okay, in this section, also linear model. Okay, linear model. And this one we call it adaptive linear neurons. Okay, linear, and how the learning converge. So this is the abbreviation version is called adaline. Okay, adaline. And here in machine learning neural network, you will see this a lot, gradient descent. Okay, a very nice way. And this adaline, it's batch gradient descent. Later on, we will also see, we will also have stochastic gradient descent. Okay, but anyway, this is batch gradient descent. Okay, so what is this? Adaline, it says adaline is first published by Widor, okay, and then later and his student Ted, etc. And it's after the perceptron algorithm, so it's an improvement. So we will see how we improve. Okay, and here there is another new concept here. So the goal for the adaline, is to what? Is minimizing, we call it a continuous cost function. So here there's another, previously we learned decision function. Decision function. Is it? That's phi. Okay, z, that's a decision function. Here we have another called cost function. Okay, what is that? And here it says minimize the cost function is basically the foundation for all of the more advanced machine learning algorithms like logistic regression, SVM, okay, support vector machine, and the regression models, okay, regression models. So what is this? Okay, the math background. Detailed is a little bit more complicated, so I will try to simplify the idea, okay? But no matter what, all we discussed here, learning, is to learn what? Is to learn weights. Is it the weight for each feature? For each feature, is it? Turn off the audio. Okay. Yeah, please. Okay, so it's to try to find the optimum way. That's the goal of the learning. Is it the goal of the learning? So here with the adaline, okay, for the perceptron, is it perceptron? It updates the weight. Weight's going to be update. Is it update? Update based on what? A unit step function. Is it unit step function in perceptron? And over here in adaline, we are not going to use unit step. We are going to use what? Linear activation function. What that linear activation function looks like is that it's basically just identity function of the net input. So this is the activation function. Activation function. Okay, that's our activation function. Okay, so basically it's just that sigma wi xi. Okay, it's the same as the net input. Okay, net input. Okay. And then, so here it shows the comparison between perceptron and the adaline. Who is that? So can you turn off your audio? Is this next time we need to verify? Okay, who please mute your audio. And the top shows the perceptron. Is it perceptron? So here we have features. Is an M feature, and this first one is for bias. Is it bias? Okay, X0 is a bias. Is it? And for each one of it, we have the weight. Is it? So this is kind of the simplest case of neural network. Is it? Then we aggregate. Is it? Then we use that unit step function, is it, to do prediction, is it? And then we will find if it is error, is it, we come back, is it, for each iteration, is it? That's how we train, is it? That's perceptron. But for linear, for adaline, so this part is same thing, is it, net input, is it? But over here, is it, over here, you see, we were going to use the activation function to do error feedback and update the weight. Okay, and after we finish off the training, then we just going to send the output. Okay, so that's the difference here. Then next, let's see. What does the cost function? So here there is a very important concept, cost function. Okay, cost function. So what is the definition for cost function? Cost function is, this is your target value. Target, is it target? Okay, for specific, so here the I for sample. This is a sample. Sample, is it? And what? This is our activation function. Activation, is it? The decision function, is it? Decision function. So basically this is what? This is predicted value. Is it predicted target value? Is it? So basically it's still y hat, is it? For the corresponding sample, is it? But this time, did you see we didn't update like last time in perceptron? It's the offset of this, then you times x, is it, times that x, and that's the delta w, is it? But this time we are not going to do that. We are going to square it. Okay, we are going to square it, and not to just stop here, we are going to apply it to all samples. That's how we count with this sigma. This is to all samples. All samples, okay. So that's the idea. So the cost function, generally we call it J, okay, big J, is what? Is the sum of squared error. Is it basically this is error? This is error, is it, the real one and your predicted, is it? So that's the error, but I'm going to add all of the error together, is it, to all of the error together for all the samples, for all samples. For all samples, is it? And this is called the cost function, okay, the sum of the squared error, okay, sum of the squared error. And if you visually view it, like suppose in this case, is it? So this represents the x, okay, we just use a single feature, and this is the y value, is it? And this kind of, you have some data, is it? Some data, is it? And what is this phi? Phi basically is some linear line. Is it linear line? So what's the arrow part? This arrow part, that's all of this, is it? That's the arrow. That's the arrow part. Is it your predicted result and the real result? Is it? That's the arrow. So over here, visually view, it's just you add all of this together. Is it to square it, add all of that together? Okay. So anyway, today we kind of run out of time. So tomorrow we will continue our discussion.